Hello, everybody. It's a bit challenging, I think, to be the last speaker. I guess you are a bit tired and you've been listening to all those really great talks. I found this conference extremely inspiring. And I get a bit jealous of the environment Christopher has. I'm the only developer where I am. So I have to have all those roles. And although I'm 55 years old, I'm not sure I am the adult in the room. I'm going to talk about controlling lab and production equipment with Python. And it was interesting when I saw the slides and I listened to the talk of Melina this morning. Because she started to talk about Öresundsbron. And that was actually one of the slides I had already in my presentation here. I have a long background working with image and photo technology. I have a background as a photographer. I've been working with printing, but I'm also an electronics engineer from Chalmers. I did some very interesting work for the bridge between Sweden and Denmark for about 10 years. And one of the first projects there, or actually the first project, was to find a way to monitor cracks in the concrete using a camera. And we needed to control that rig with the camera. That is a motorized rig there. And I looked at the internet trying to find something, and I found this lovely open source package for doing just that. It was written in Python, I think it was Python 2.7, but it did not have a driver for this rig. It had everything but a driver. So that was my first encounter with Python. And after PHP, C, C++, and other things, I fell in love quite immediately, although it was still Python 2.7. And I did a lot of different projects for the bridge. More and more about monitoring things using sensors. And that is where I found that you can do a lot of fun things with this. This is a Raspberry Pi. How many here in here have ever played with a Raspberry Pi? Oh, this is love. And my current client is LuxBrite. They make X-ray tubes. An X-ray tube could look like this. It's like the light bulb in an X-ray machine. So we apply high voltage, some low voltage here, make it glow, and you get X-ray. Don't worry, you will not get radiation now. And the reason why they brought me in as a consultant, because I'm running my own consultancy company called Oddtech. I have another company called Digitalfotografen as well, was to help them with testing X-ray tubes. That means that we take some pictures, and I made an automated, I made some Python scripts for automatically analyzing those pictures. But when I came out in their research lab, I was first a bit scared, then I realized, oh shit, we have a lot of room for improvements. They were manually running the test, tweaking knobs on high voltage supplies, writing down results on paper, feeding it into Excel. So I told them, I think we can do some automation here and make things a little bit more fun for you. About fun, one of the really fun things about working with a company that does X-ray equipment is that you get to X-ray things. So if you ever wonder what an Apple laptop looks like inside, this is this very laptop. In the middle you can see the CPU. Down here in the bottom you can see the batteries. And at the top it's the screen. And you can see like there is some shadow pattern, and that is the keyboard. This is what an iPhone looks like when you put it in the X-ray. So in the bottom you see the cameras, it's the big battery, some of the electronics. my current or my newest project is to automate the operation of this laser welder. Let's see, there should be a playing, yeah. So they are doing a vacuum tight weld on the end here. And that rotates, and that is controlled by a Raspberry Pi as well. And also when the laser is switched on and off. And there is what is not shown in the video here, that there is a touch panel running a Kiwi user interface. And the operators, they love this. It's not very many lines of Python code. Most of it is for the user interface, actually. Well, my goal with doing this presentation, I have two goals. The first is to inspire you to do fun things with hardware, using your Raspberry Pis to control things that you would have use for. Is there anybody here that does beer brewing? Okay, there's a few. Is there anybody here that has a greenhouse or does some growing of plants? There is some as well. Okay, I will have some hints for you during this presentation. For you others, find a project where you need to do something with hardware. It's a lot of fun. And you might get interesting jobs with it as well. Let's see, it's stuck here for some reason. Okay, so one of the things I've done for LuxBrite is a control and data logging framework. Unfortunately, it has built it in Tkinter. If I would do something different, I would use Kiwi or something today. But they use the same framework for the X-ray lab, for when they do production, where they run vacuum pumps and furnaces. And the nice thing is that the operators, they work at a lot of different stations. And they feel comfortable because they see the same kind of UI. But what is inside will differ depending on the station. So it's modular. And I use like one Raspberry Pi for each function. So if I have vacuum pumps, we have one Raspberry Pi doing vacuum. Then we have another one controlling heating, and another one maybe high voltage. So we build it up modular. So let's start with lab equipment. I forgot to tell you I had a second goal, actually. Sorry. My second goal was to find other people that do similar things with Python. So if there's any one of you that does a little bit similar things, please come and grab me after the presentation. Since I'm the only developer here at this company, it's always fun to talk to people that do a bit of similar things. I've already found a few of them here. If you're into electronics, then you might have a small lab bench with some power supplies, some multimeters, maybe a spectrum analyzer, oscilloscope. Almost all of them today, if they are like a bench model, will have a serial port, USB port, or an Ethernet port at the back. And that means that you can actually control them. The common way to do this is with LabView. That's a commercial software. I think a license is about 25,000 Swedish kronor per year, and developer, quite expensive. It has a lot of nice features, although I prefer Python. But the good thing with that has been very dominating for a long time is that a lot of instruments supports LabView and this virtual instrument software architecture protocol. So almost any instrument you buy will support this protocol, and that means you can control it from Python. There is a library called PyVisa that can work over this protocol. And there is on top of that a command language called SCPI that is not really strictly standardized, but it's not a big problem. The important thing is that the hardware layer, the network layer is standardized. And you see here, this sample script here, is for controlling an instrument like you see here, a multimeter that you can hook into and measure voltage or current and other things. And it's only a few lines of code needed to start to read something from the instrument. So what I do here in the init method here is that I create a resource manager and I tell it that I want to use the Pi implementation. There is a string called the connection string. I made it global here just to fit it somewhere. But you can see it as TCP IP. That means we want to connect to the instrument over Ethernet. It could be serial otherwise. Then it's the network address. You could use the domain name, although you might not have a domain server for just your lab. And then we want to use port 5025, and we want to use a TCP/IP socket. So we put it in as the resource string in a resource manager, and we get a device. That is what I call here DMM current. DMM is digital multimeter. You can have multiple devices to the same resource manager. So we could hook up like a power supply here as well, or an oscilloscope to the same resource manager. And then I tell it with the configuration string here, I want to read current, I want to have a range of 2 milliamps. And then we can start to call the next method here, measure current. We send an init command that is telling start sampling. And then we send a readout command and we get the voltage back. You can also put it in a continuous mode where it will sample and then you get a block of data each time. So it's only a few lines of Python code and you can do this. There is 2 lines here that I want to emphasize. It's this RST command and the CLS command. Always start with that, because that clears the settings of the instrument and puts it into a known state. Otherwise, you don't know what somebody did with that instrument before, and that will otherwise affect you. And you could use a context manager. Here I have a close method instead, and it's not always suitable to use a context manager because you might want to sample for a long period of time. This works really nice with PyTest. So if you spoke with somebody else who were producing electronics and wanted to test their cards, you can use PyTest for testing electronics. Hook up your instruments, run PyTest, and get a report. So that's another use for PyTest. So we use this for some equipment in the lab that supports this, like some of our high voltage supplies. And also when we test this filament that's inside here, then we use a power supply. I think it costs like 3,000 kroner from Sigilent, together with something like this and automate the tests. It works really, really, really great. Okay, 2 years ago, originally they were not making the X-ray tubes in Sweden. They were using OEM manufacturers in China. But 2 years ago, they said, no, we are going to move the production to Sweden. And I had made a lot of automation in the labs, using a lot of Raspberry Pis to control high voltage supplies, stepper motors to move things. And now they said, can you also automate the factory, this micro factory? And I was thinking, okay, that you would normally use a PLC for that, program and logical controller. It's not very complicated to use those, but we already had a tech stack with boxes like this. In each of those boxes, there is a Raspberry Pi, there is a power supply, there is a DAC card. I will explain DAC card soon. And we use more or less the same box for every function. It's just the different software and different configuration. We have 2 other boxes. We have one for stepper motor control, and we have another one with a lot of temperature probes also that we use with furnaces. And the production manager, he said, can't we reuse the same infrastructure? And I said, let's try it. So we started actually to use those Python programs, this framework I told you, for running the factory. That meant I needed to hook up with a lot of industrial sensors, and I did that at the bridge as well. An industrial sensor can be something like this. This one can measure distance. It is a laser, and then there is a contact. And the typical thing for industrial sensors are they're quite rugged. They run on 24 volts, and you can get the voltage or current signal that is like the level out there. And it's usually between 0 and 10 volts, or you get a current between 4 and 20 milliamps. So it's really easy to interface with those. And then this is a more advanced one. You can also do serial communication with that. But if you want to measure like the level of a water tank, you can have something like that measures where it is. Or you can use ultrasonic sensors, or there is a lot of different sensors, pressure sensors, that works like this. Some of them will give a pulse train, like if you measure flow of water, you will get a pulse for like every milliliter or centiliter or something. And this is really easy to handle, but not for a Raspberry Pi. Not alone. First of all, don't connect 10-volt signals into this one. It will fry. And it doesn't accept analog signals. But the solution is easy. You get something like this. This is a DAC card, a data acquisition card. There is different brands. We usually buy from PyPlates. They have a lot of different ones. You stack it to your Raspberry Pi. This costs, I think, 800 or 900 kroner. This has 8 analog inputs, 4 analog outputs, 8 digital inputs, 8 digital outputs. And this can handle those voltages without problem. There are other boards like the one I'm showing here that might have some relays. That is really nice for hobby work, and you can get cheaper cards like this, because with a relay you can control like a heater for your beer brewing or for your greenhouse or a water pump. And they are easy to use as well. You see some sample Python code. This is a silly but simple project. Let's imagine you're going to fill your beer brewing tank or a water tank in your greenhouse. So you have one of those level gauges. You can measure the pressure at the bottom or something. And you have a pump, and a pump is typically on and off. So then we can call this card, the DAC card there. You get a global instance. And the first method here is for measuring the level. So we just get call ADC, tell that it's card, the address of the card, and then what channel we want to measure, and we get a float back between 0 and 10 that you might have to scale then to what is the level. And then for the pump, it's just a bit that we clear or set to turn it on or off. And you could probably drive a small water pump with this one actually. And then we have a loop at the end here that is like our control loop. We put in the level we want to have, we switch on the pump, and we run until we are up at the level. So only a few lines of code to fill a water tank or something. So it's quite nice to play with. It's really, really fun. If you want to measure temperature, that is quite common. Very important for greenhouses, very important for beer brewing. Then you can get something like this. This is a one-wire thermometer. You can get them at like Cello Company across the street. The nice thing with this one is just 3 wires, one for ground, one for plus voltage, and one for data signal. And if you want to measure temperature at a lot of spots, you just connect them in parallel, like a bus. And each of them has a unique factory configured address. And you just use a loop like this to scan the bus for all the devices and get the temperatures out. Then you can memorize the addresses and use them to measure temperature at different places. We use this actually in our greenhouse to monitor heating there in the spring to make sure things doesn't freeze, and we have similar things for watering done in Python, and also we have one of those DAC cards for some stuff. Another thing you might need to look at if you're doing more serious things, like for industrial use, is serial ports. They might look scary in the beginning. Some of you are old enough to have used a dial-up modem for internet access. Then you had this RS-232 port at the back of the computer. That kind of communication is still common in the industry. And if you have a laptop today, you don't have a port like that. But you can buy a cheap USB adapter, and you can start to communicate with those. And quite often the protocol is unique for each device. You need to look in the user manual for them. But it's quite easy to communicate with them. Here you get good use for the async and await, the asynchronous communication in Python. Because you will send a command, it will take some milliseconds to get it back, sometimes worse. And if you use it as async and await, your program can do something else at the same time. So this is a code sample for doing that. One advice when you talk to serial devices is to actually use some kind of lock. At least if your software might try to do multiple things with the same device at the same time, because they usually don't like when you send several commands to them without taking handling the response first. So that is one hint here. Okay, some challenges when talking with hardware, because it's a bit different than when you do web programming, and like we had the speaker before him telling me about his nice CI/CD systems. That might not work here. You might have to do things different. You still should do a lot of testing, but don't expect to get the same result every time you read a sensor. You might expect it to give the result 5 volts every time, but it will sometimes be 4.999995. Next time 5 point. It will differ. You will have noise. So don't make exact comparisons. Always have like a threshold or a range. The same thing when you switch on. You might need to have a threshold that, okay, I'll switch on when it goes above this level, but then you have a margin for when you're going to switch it off again, or your relays will click on off, and burn out. Timing problems. Your reply on a serial port might sometimes take 1 millisecond, next time take 10 milliseconds. And you might, if you talk to a lot of equipment, the sequence of the responses might be different from each time. So you must handle asynchronous events. And tests might be slow. We have furnaces or pumps. We have turbo pumps. It takes 20 minutes for them to spin down. So if I'm going to test the sequence where we spin it up and spin it down, I need to run those tests, and it can take hours. And I might not always have access to the equipment. Don't forget safety. Okay, I'm in a place where everything is dangerous. We have 200,000 volts. We have deadly gases. So that is extreme. It's a little bit better in your greenhouse or in your beer brewery. But at least make sure you can switch it off by some different way than just the software. Have some safety on the hardware level and in the software level. And remember Murphy's Law. If something can go wrong, it will, and not in the way you expected. If somebody are interested in this framework, we plan to release parts of it as open source, but we need to clean out the stuff that is company dependent, and we need to make better documentation. But if anybody's interested, you can come to me. I will put this presentation at, I think I wrote a GitHub link down here. If somebody's interested, you can take a picture. And thank you very much. And I hope you will go home and play with your Raspberry Pis, do some fun things, make some noise or pump some water, brew some beer. And thank you for a great PyCon.
Thank you very much for the talk. So we can take some questions. Any questions? Yes.
Hello. Yes, can I be greedy and not ask only one question?
Yeah.
Yes, first thing, are you aware of HPK and IMC data acquisition systems?
No, not really.
Yes, they are like, I work with testing, and I test accelerations and forces on trains, and they use these systems, and this might be interesting. A second thing is, I know someone who plays with lasers in France. They have made I think they created an open source Python library called PyMoDAC, if you have heard of it.
No,
Not
that's
either.
also, but that is also one of the reasons for me for coming here is to learn. What was it called? PyMoDAC?
PyMoDAC, it's like modular data acquisition in Python, and it's also aimed to connect, the library is written to connect to different national instrument modules. So it's, and I think they also cited, what was it called, Visa?
Okay.
A few slides back, but it's interesting to see parallel development. Yes.
Yeah. I also heard, I think, I'm not sure where it is. I spoke to another guy. He was telling me something about a library called Tango. Yeah, you? Was it called PyTango or PyTango? That I also need to test for this. But these measurements you were doing with the trains, is it like for electric fields and emissions, or?
It's for running dynamics. So to make before a train is actually allowed to run somewhere, you will test it so it doesn't derail or it's not too uncomfortable for passengers. And I'm curious about the pie plates. How fast can they sample?
Not really fast. About, if you do one channel, I think you can do like 600 samples per second. And if you use multiple channels, then that's it slows down. The poor thing with them is that the Python library is not very well written. I've tried to communicate with them. I've given them some hints. So we will actually start to design our own DAC cards. I'm not sure about this MCC. I haven't tried them, but I think they are faster. Mm-hmm. But it's not really that difficult to make your own card if you would need. And we'll probably do our own card now to get faster sampling. But about 600. But for most of the stuff we do, we are running around 100 samples per channel, sampling like 2 or 3 channels. So for us, it's usually not a problem. But the problem with the Pipeless driver is that it's written in a stupid way that when it's waiting for the sample results, it locks the thread. It blocks the thread. So you lose a lot of CPU power. That is what I've been complaining with.
All right. Thank you so much.
I think we can take one more.
Yeah, so I'm just curious, what is the most expensive thing you've broken?
Oh! Well, it's a high voltage power supply. I think the price for it is like 50,000 kroner, but it was repaired. So it was not that I lost it. And the problem was that I broke it 3 times. And every time it took like 14 days to get it back. And it was because when we got arcs, we were getting high voltage pulses out through the ground, and yeah, I learned a lot about how to handle spikes and use those transition TSV diodes on almost everything, and also ground everything. So not that bad, I think.
It could have been a lot worse.
Yeah, for sure.
Okay, let's thank the speaker again.